right. Hello, everyone. Welcome to today's webinar. My name is Jenny Selway, and I'm the CEO of HILT CRC. And you're joining us today to hear our webinar on optimising energy infrastructure development to provide reliable, affordable, clean energy for industrial hubs. So we'll have a presentation first from Dr. Tara Hosseini from CSIRO on one of our energy infrastructure projects, and then a panel following that. Next slide, thanks, Adam. So firstly, I'd like to kick off with an acknowledgement of country. I'm dialing in from Melbourne today. So I'm situated on the land of the Wurundjeri people of the Kulin Nation, and I pay my respects to elders past and present, and acknowledge the traditional owners of the land across all of the country, because HILT's a national organisation, so I know everyone will be dialing in from various locations. And so particularly here in the Wurundjeri land, very cognizant of the impact that Aboriginal and traditional owners have had, and really wish to pay my respects to elders past and present. Thank you, Adam. So just a quick agenda update. So Dr. Tara Hosseini from CSIRO leads our 3.007 project, looking at energy infrastructure. It's part of our Program 3, Facilitating Transformation. So HILT, which stands for Heavy Industry Low Carbon Transition, looks to decarbonise iron ore, steel, alumina and cement sectors. And we have 3 research programs to do that. One very focused on technical projects, one on cross-cutting projects that looks at commonalities between the sectors. And we have a lot of energy-related research in that program. But we have a third program called Facilitating Transformation, which is everything that's not technical, and things like policy, regulatory, and development of green markets, and also enabling infrastructure. So this particular project, although it sits in Facilitating Transformation, also has very close ties to cross-cutting technologies, because access to clean energy at scale is commonly referred to as the #1 barrier for heavy industry decarbonisation. So this is one of our largest projects that we have in HILT, because pretty much everyone is very interested in it, because it's so important. So it'd be fantastic to have the update from Dr. Tara Hosseini on that project, and then followed by the panel introduction from the panel featuring Professor Gus Nathan, our Research Director, Mitch Burt from South 32, Wayne Harris from OneSteel, Kim Enkelaar from RecFit, the Tasmanian government, and Ben Saward from Grange Resources. So a really lovely mix of all of our partners across research, industry and government. We'll then follow that with an audience Q&A and summary and key takeaways. So there is a Q&A section on the chat where you can put your questions. And that's all from me. I'll pass over to Tara for her presentation. Thanks, Tara.
Thank you very much, Jenny. Hello and good morning and good afternoon, everyone. Thank you for joining us today. And I would like to extend my warm welcome to everyone that's attending this webinar, and also to our panelists as well. So I'll start by sharing my screen to just giving you a quick overview of the project. Can you please confirm that you see the screen right? All right, so thank you, everyone. So as Jenny mentioned, so I'm going to talk about the unlocking investment in energy infrastructure for net zero industrial hub. So this is the project that we started around a year ago, and this is one of the flagship projects in the HILT CRC. So I would like to start this presentation by acknowledging and thanking all of the project research team, which you can see their names listed on the first slide. We have over 25 researchers across 5 research organizations working on the project, and we have over 10 industry and government partners that are working with us on this project. So to just give you a bit of background about this project, so the transitioning to net zero energy system will require a significant investment in new energy infrastructure. So this transition needs a phased approach. So we can't do the decarbonisation overnight. And we have to start by adopting the technologies that are currently closest to the market, and then gradually transitioning to the technologies that are currently under the development. This transition also has to be in alignment with the progressive transition of the sector. For example, we need to consider the stage increase in the production capacity for each of these industries. And also it has to be in agreement with the target emission reduction that is set by the Australian government. So as you can see, we have a decarbonisation timeline and we have some milestones along the way. So we have to make sure that we are following that timeline as well. So as you can see, the technology that we are developing and we are proposing for this decarbonisation, we have some short-term options, medium-term options, and long-term options. So as an example of the short-term options could be adopting more energy-efficient technologies, or for example, using transitional fuels where possible. The transition of Australia's heavy industry sector to net zero carbon future demands a comprehensive and regionally specific approach to energy system transformation. And that's the reason we are considering a hub-based approach. So as you can see in the right-hand side graph, we have identified locations for our heavy industry energy hub, which is based on the locations of our heavy industry, and the prioritization is based on the heavy industries that are involved in the project and also involved in the HILT. So to just give you a bit of background about the structure of the project and the link to the existing project, as you can see in the middle, we have 5 different work packages. And these work packages are very much interrelated. So in work package 0, we are working on developing our decarbonisation scenario, which is through a very extensive stakeholder engagement process. So we start with a small group of people inside HILT, and then we are transitioning to consulting outside the HILT as well. So once we develop these decarbonisation scenarios for the alumina and for the iron and steel, for example, reference scenarios and alternative scenarios, we are moving to the next stage, which based on the developed scenario, we will be identifying the regional energy demand. So the type of energy that is required, if it is in the form of electricity, hydrogen, thermal energy, or for example, natural gas. For package 2, we'll take this input to do the regional energy supply assessment. So what is the optimum mix of hydrogen and different types of energy, and how we can optimize the cost of delivery of this energy supply to different locations. For package 4, we'll take the output of for package 1 and 2 and is integrating this energy demand and supply to come up with a unified model to do a further optimization. And for package 3, finally, is looking at the infrastructure investment option, for example, the co-investment by the government that may be justified based on the, for example, future economic benefits such as employment, social and regional benefits, and etc. And also, as you can see here, we have a link to the existing project. Some of these projects are still in operation in HILT, and some of them are finalized. So for example, if you have a look at some of them, hydrogen iron making, so we have lots of projects about thermal energy storage, hydrogen supply, electricity supply, biomass and bioenergy, and CCUS as well, that we will be using as an input to this project. So here I'm just showing one example of the proposed scenario for net zero gibbsite rich alumina, which is based on a low temperature and pressure digestion. So the process is basically based on electrification and also steam recovery. So as you can see in 2025, if you can have a look from the left-hand side, it's business as usual. So we are using fossil fuels currently for the bioprocess and for the calcination process as well. In 2030, we are implementing electric boiler to replace 10% of the heat demand in the bioprocess. In 2035, we will add another 10% of the heat demand, which is coming from electric boiler, and we are also implementing a partial steam recovery. So for example, we do a steam recovery from evaporation step in the bioprocess, which is giving us about X% of the heat demand, which based on our calculation and some of the project that has been done in HILT CRC, this is about 39%. In 2040, we will be adding another 10% of capacity of the electric boiler in the bioprocess. And at the same time, we are adding a partial electric calciner to replace about 50% of the energy demand of the electric calciner. In 2045, we will be completing the partial steam recovery to be the full steam recovery, which is again giving us about 5% offset of energy, which based on our calculation is about 70%. And the rest which is about 30%, is coming from the electric boiler, and we keep the partial electric calciner as 50%. And in 2050, when we move to net zero emission, we will have a full electric calciner implemented in the calcination step. So this is the proposed scenarios for one specific type of operation. So we will be developing some other scenarios for example, high temperature and pressure digestion as well. And it has to be further refined based on the regional requirement, and also is going through our stakeholder engagement process as well. So now here I'm showing one example of the reference pathway for the net zero steel production as well, which for this one is based on the magnetite ore, and it's our proposed scenarios for the Viola case. So as you can see, we are proposing two scenarios here. So one is based on natural gas implementing CCS to the process, and the second one is based on natural gas transitioning to the hydrogen DRI process. So in the first pathway, so we are implementing the natural gas DRI with EAF process. In 2040, we are implementing the CCS to the process, and 2050, because we need to have net zero emission and we can't really capture all of the CO2 emission from the process, we are implementing a biomethane into this process as well. In the second pathways, as you can see, we are starting from natural gas DRI due to some of the limitations that the hydrogen DRI process currently have because of the cost and some of the metallurgical challenges. We start by transitioning from the natural gas to the hydrogen. In 2040, we are replacing 70% of the natural gas with hydrogen, and that's the reason because the carbon that is available in the natural gas is chemical, can favor the EAF process, and that's the reason that we have started with 70%. And in 2050, we are replacing the rest of the natural gas by biomethane. So I mentioned about these scenarios and also the demand of this, the energy for these scenarios that we have developed. Now we look at how we can develop a hybrid energy supply model. So as you can see in the left-hand side, so we have a system, integrated energy system, which is including input of the solar power, solar energy, and also the wind power into the system. So we are implementing all of the conversion of the energy, the storage, different types of storage you can see we have. And this system will optimize and give us the lowest cost of energy delivered to the users. The objective function, as I mentioned here, is to minimize the level of cost of energy. The model is a linear programming model, which is developed using Python and Minizing to obtain the optimal solution. In the right-hand side, you can see how we are considering the location, because we need a spatial resolution for location-specific renewable energy, for example, and also to take into account all of the transportation and transmission as well. So what we are doing here is we are using a total scoring criteria, which is based on the approach that AMO has used in the ISP, and they have developed some renewable energy zone that we are also, again, using the same methodology. The right-hand side graph is showing the scores of the different regions based on, for example, the renewable energy availability, proximity to the other infrastructure, and also land availability as well. And then we select a top 30% scored map to do the further optimization of our system here. So work package 4 is integrating the energy supply and demand into a single operational model. So here we are using a model-based system engineering, or MBSE, to develop a holistic, coherent, and a scalable multi-energy model. So here the aim is to convert our work package 1 and work package 2 models into a more unified model that could be used for further optimization of the process. So the expected outcome of these projects, so as I mentioned, so regional energy assessment. So we will be working on tailored energy demand and supply projections for regional hubs, with considering factors like industry type, technology adoption, and product development. And we will be working on investment prioritization. So for example, what is the cost-effective infrastructure, by identifying the optimal energy for each hub and considering factors like technology, timing, and total cost, and co-investment justification and the regional benefits. So the integrated energy system can efficiently manage the energy supply and demand across different sources and users. And finally, we are aiming to have technology adoption and de-risking by helping accelerating the technology deployment and also de-risking and removing the barriers such as cost and uncertainties. So that's all from me. Thank you very much for listening. I try to be quick, and I think maybe I just went over a little bit over time, but thanks for listening. All right, so thank you very much, everyone, for listening to this presentation. So now we are moving into the second part of this webinar, which is our panel discussion. So before I ask our panelists to introduce themselves, I just would like to add just a bit of introduction. So we know that the transition to net zero emission is an enormous challenge, and also is a historic opportunity for Australia's heavy industry sector. So we know that the heavy industry is the backbone of our economy. So the decision that we are making today regarding energy infrastructure, technology adoption, and also regional coordination will define the success and competitiveness of these industries for decades to come. So that's the reason it's very important. And now, I would like to say that we have invited an exceptional group of leaders and experts to share their direct experiences, critical challenges, and future visions. So now I would like to invite our panelists to please introduce yourself, tell us a little bit about your experience, your role, and your organization. So I start, so I'm just wondering, Adam, if you can, yeah, thank you very much. I'll start with you, Mitch.
Yeah, thanks, Tara. Thanks for the introduction. So, g'day everyone. My name is Mitch Burt. I'm at South 32. I sit within our technology development team. My role is practice lead for decarbonisation technology. And within the HILT CRC, I'm also the industry chair for Program 2, which is our cross-cutting research program. And as Tara and Jenny have both mentioned, Program 2 actually has quite strong links with this research project. Yeah, which makes it quite an exciting project for me. My background technically is mechanical engineering. I spent about 10 years or so in the mining industry in various operational roles before I moved into this role in 2021. There, that's probably about enough from me. Thanks.
Thank you very much. Bain, please.
Thanks, Tara. Thank you. My name is Wayne Harris. I work as part of our transformation team, as part of OneSteel manufacturing. So we're working on the transition of the Whyalla Steelworks to a low emission future iron and steel making facility. And we've been part of HILT for quite a while across all the programs as a core member. So this is very much a project that we're certainly interested in, and we can see the alignment with where we're going as well.
Thank you very much. Ben, please.
Hey everyone, Ben Saward, Commercial Manager at Grange Resources. So yeah, we're an iron ore mine, magnetite, Tassie. Been around for 60 years. Actually have a pipeline that pumps that in a slurry to our pelletising plant, where we make iron ore pellets and ship all around the world. So yeah, my role is energy and strategy projects is part of my brief, and over 20 years, I've developed many different contract models to address electricity and gas, and obviously looking at decarbonisation journeys as far as removing our diesel, being the largest user of diesel in Tasmania, largest user of natural gas in Tasmania, one of the largest users of electricity. So we've got, a pretty challenging decarbonisation plan, and certainly the work that HILT's doing to look at all the avenues that we have is very much appreciated, and enjoy my involvement on a few other projects as well. So that's pretty much me.
Thank you very much, Ben. So Kim, please.
Good afternoon, everyone. My name's Kim Enkelaar. I'm the Director of Future Industries here in the Department of State Growth in Tasmania. So our team's part of the energy part, if you like, of RecFit, which is Renewables, Climate and Future Industries Tasmania. And in fact, I think the coupling of renewable industries or future industries, climate and energy is quite unique in Australia, and that's part of what makes Tasmania so special, and so able to really understand both the challenges and opportunities that a net zero transition may be able to provide for our state. So our role is to provide advice to government, but also run programs to enable and facilitate both current industries like Ben's at Grange Resources to help them transition to net zero, but also support new industries, so such as hydrogen, other future clean fuels, assist all industries across Tasmania. We are great supporters of HILT through our climate change team as well, and it's really important for us to be able to be part of the conversation today, and most importantly to listen to industry. But thank you very much for having me as part of the panel.
Thank you very much, Kim. So Gus, please.
Yes, good day everybody, and thank you for dialing in. So my name's Gus Nathan. I'm a professor in mechanical engineering based at the University of Adelaide, but also seconded as the research director for HILT CRC. And my background is in energy and the use of it into industrial processes. I've spent a lot of time on industrial plants around the world and developing new technology, and started in, I guess, lowering different types of air pollution such as NOx emissions, and then as the challenge shifted to industrial decarbonisation, then that's also where I shifted. So I work in that area, and also with alternative fuels and including hydrogen as key enablers. Thank you.
Thank you very much, Gus, and everyone. So before we start the questions, so please, again, if you have any questions, please put in the Q&A box, and we have some time at the end of the panel discussion to answer some of your questions. So I start my first question with you, Mitch. So my question is around the importance of the outcome of this project. So how do you see the outcome of this project helping you address the need for low cost, low carbon energy in South 32's alumina refinery?
Yeah, thanks for the question, Tara. So I guess in general, South 32 view the HILT CRC research as a key vehicle for us advancing low carbon technologies. And through our internal work as well as the HILT CRC research, we've recognised that infrastructure under various different pathways is a key issue that needs to be addressed. And this research project in particular, is really key to addressing that. I guess more specifically, the outcomes for the project, there's going to be a few that are going to be quite relevant for us. So firstly, gaining a more detailed understanding of the infrastructure requirements for our region, which is in the southwest of WA, where our refinery sits. Under different technology pathways, and then also understanding what the optimal regional infrastructure solutions are from a cost perspective, and I guess importantly from that region perspective, as opposed to optimize for one particular operation, which is something that's quite hard for us to do as an individual refinery operation. And then, I guess another important insight is the investment options to fund those infrastructure investment requirements. Having a better understanding of what those investment options are is going to allow us to have more constructive conversations with the stakeholders within our region. which includes other heavy industry participants who potentially are, looking to go down similar decarbonisation pathways. The government agencies, network operators, and the regional communities as well. But at the same time, we also recognise that a lot could change, in the coming years as the energy transition unfolds. And so we look to actually adopt those tools and refine those assumptions and refresh our thinking as this energy transition unfolds, so that we can help make better informed investment decisions.
Thank you very much, Mitch. So if I want to just highlight one of your points that you mentioned, so understanding the investment option is critical for enabling a constructive, informed decision with all of the stakeholders in the region. So it's very important and is a good, point and reminder for us in this project as well. Thank you very much, Mitch. So I'm moving to the first question for you, Wayne. So the question is around the same kind of, concept. So the main pathways that is discussed for the green steel production at Whyalla is through the DRI and EAF process. So what do you see as the key technical and also the commercial challenges of going straight to the hydrogen-based DRI or transitioning through the natural gas?
Yeah, thanks, Tara. I guess maybe when we sort of talk about some of the challenges, maybe a good way to start is to look at a bit more background. So we've been working on the transition to low emission iron and steel for quite a while now. And so when we look at there's a number of key ingredients you need to consider, and they all have their own challenges, but we've been working on this for quite a while. First of all, it starts with the ore, and we're fortunate enough in South Australia and with OneSteel to have a significant high quality magnetite ore. And in fact, we've been mining in South Australia for over 120 years, and the last 16 years that includes magnetite as well. And so this has meant we've spent a lot of time de-risking and working through the processing of that ore, and are able to develop a pellet that's ideal for magnetite. So high iron, low silicon. And so for us, that's taken quite a while. It's because of all of the work that we've done. We've also tested that pellet across the globe with high results. And so this is first important part of that de-risking and the challenge to get through. The next part of the ingredients are around the direct reduction process. And direct reduction processes have been in existence since the 70s. In fact, estimates are about 7% and growing of facilities being built across the world. So it's not new, and actually using it with natural gas and reforming that into hydrogen, technically, you could say, is not new as well. So this means as we move through this, the technology has also progressed to be able to use both natural gas and hydrogen together, which is exciting for us. And part of our transition, we'll look at how we move, first of all, from a blast furnace process through to a natural gas DRI process, and then into hydrogen. Now, of course, if you understand steel, you do need to have some carbon in there at the end. And so a mix of natural gas and hydrogen might be the ideal way of doing that in a smooth blend into the process as well. The next other ingredient, of course, is electric arc furnaces. Now, they've been around and growing across the world. We have 2 in Australia as well. And we'll see more of that, and the impact of addressing renewables in those areas will help decarbonise those pieces as well. There are other areas in the ingredients as well, such as the market end as that develops for both HBI, so hot briquette iron product, which is prior to steel, or also for end steel of low emissions. This is both domestic and internationally, and there are other parts that are emerging and developing. As is, we're fortunate enough to have the infrastructure and the people in place already in the community in Whyalla. This includes the port and rail. So a lot of the ingredients are already there, and we're very fortunate in that respect. And also with the government support, there's also around and looking at the future. Of course, the other area that's related to this project and very important is energy. And so when it comes to energy, that includes natural gas, electricity, and also hydrogen in the future. Now, we're fortunate enough to have a pathway for that, but it is a big step. This is not just the natural gas, it's the infrastructure, it's the molecules, it's the electrons, and it's increasing in scale of what we need for that into the future. And so when you look at the challenges commercially and technically as we move forward to this, you need to look at it holistically and also on a step-by-step basis through each of those ingredients. Just as an example, one dynamic to look at it is the logistics. Another is to look at the markets. You're moving away from a market that's based on a coking coal cycle to now an energy cycle for natural gas or electricity. So there's many dimensions that we need to look at. They're all challenges, but we need to go through them sequentially, step by step. Thanks, Tara.
Thank you very much, Wayne. So I think the point that you mentioned about, utilizing natural gas and hydrogen would be beneficial for the EAF process is very good to know. Thanks, Wayne. So I'm moving to you, Ben. So how do you envision the integration of new energy sources, such as hydrogen or renewable electricity, with your existing plant operation? And what are your main concerns regarding the reliability and stability of these new supplies?
Yeah, no worries. So obviously, yeah, diesel's a big one for us in our mind. So, and maybe one of the easier ones. So obviously we're moving from an open pit mine to an underground block cave. So from diesel to electricity in that underground mine. So an extra, say, 21 megawatts to bring us up to about 55 megawatts. So that's proven technology as far as electrifying underground mines. We're applying some other smarts to that as well. So getting that infrastructure set up is one of the challenges as far as reliability and getting the supply. So, it involves upgrading transformers, building new feeder lines, and then putting the whole conveyor and electrical system in, charging and whatever in the underground. So we're comfortable with that, but it's just one of those that needs to be respected by industry, is how long the process can take when it comes to upgrading infrastructure, being transmission assets or transformers, given the long lead times. It takes a long time to get those providers to do their studies, and other things that can complicate that is if they're common use sort of transmission assets, and many of those are at full capacity at the moment. So there's a lot of augmentation investment that's needed to, you have businesses that individual load cases, but they rely on the network planners to submit their revenue proposals and get approvals. And then sometimes those timelines to do that, and then the construction timelines don't always fall in line with businesses' goals or the small windows of opportunity. So thinking about that transmission infrastructure side of it early is key. So that's diesel. Then when it comes to sourcing electrons, as part of that, that's a challenge as well. There's growing sort of demand for the capacity that we've got in Tasmania and in other states. And if you want a lot of electrons, you're going to be forced into PPA arrangements on wind and solar and the likes that do come at an additional cost that many haven't faced. So basically that desire for those renewable electrons is growing, and being driven by things like the safeguard mechanism that we're a part of, and that's driving behaviour so we don't pay carbon tax, effectively decreasing those emissions. So diesel's not too bad there, but it's the price point with the electricity as well as getting the supply that's crucial there. Same applies to our furnaces. So we need an extra, say, 50 megawatts to electrify those furnaces. And likewise, that'd have to be supported by PPA and upgrades to the grid. Hydrogen, we've certainly done many studies there. We need 100 megawatts, which isn't easy to get, to produce, say, 16,000 tonnes of hydrogen to replace the 2 PJ or 2 million gigajoules of gas that we use at the moment. So we could build an electrolyser on site, very expensive, or deliver the hydrogen. So, that's not always ideal where hydrogen's going to be produced in hubs like, say, Bell Bay. It's totally unviable to build a new pipeline. Yes, you can blend in existing natural gas pipelines, but only to a certain percentage, which doesn't really achieve your objectives. So, at the end of the day, to replace gas viably, it needs to be about $2 a kilogram hydrogen. And as we're seeing with traditional production approaches, somewhere around $8-9 a kilo to produce it. But if you get hydrogen head start funding, that can come down to nearly, say, $4 or $5. But that's the challenge, is the cost of hydrogen at the moment, and we've seen many projects sort of be stalled because of those imposts. But it's encouraging to see new technology, and I guess that's where research play a very important role, because I think it's technology change that's going to drive the viability of decarbonisation for industry, more so than just saying we'll build wind farms and solar farms and all this transmission assets to help the industry decarb, because we can't afford it to compete globally. But there's other startups like Polar Blue that are saying they can do hydrogen under $2 a kilogram, and they're starting to sort of roll that out, and they've got storage and delivery solutions that make that deployment possible anywhere. And then the last bit around that is the securing of grants to help you fund some of these initiatives. They're great, but the timelines and reporting requirements are quite strict, and as we know, projects do experience delays all the time, so it's being nimble with governments to be able to sort of change those goalposts to still maintain your grants and keep your project alive.
Thank you very much, Ben. Very good points. And the cost of hydrogen, I think you mentioned that as well. So that's a global challenge, I believe. So I go to our next panelist, Kim. So my question is mostly around the collaboration. So given the project's focus on regionally specific scenarios for heavy industry, how can a state government and industry can collaborate to ensure that the localized energy transition plans align with and also support the Tasmania's broader energy and economic strategies?
Thanks, Tara. Great question. And it's actually a question close to my heart. I absolutely truly believe in honest, open and early collaboration is really the key to unlocking how we can work together and for mutual benefit. If I go back though, energy is so complex and the clean energy transition will be expensive, as others have pointed out, and take time. In Tasmania, it took 70 years to be self-sufficient in renewable electricity, and now we're looking to double our electricity in a third or less of the time. And why we're getting on with it, and there is no doubt it is going to be a challenge, governments don't hold all the levers, but for me it's about how we go about our engagement and our approach with industry that will actually help us try and achieve, as I said before, some mutual outcomes. So in terms of my experience in working in this sector over the last 5 years in particular, co-design as much as you can and as early as you can. So be really clear about what the joint objectives are with industry and with government and with community and with business and with your environment, with thinking about workforce. You really understanding what are the joint objectives and what does success look like across the whole value chain. And if you can start with that, you can start with where you can agree and you can move forward with that. For me, in terms of collaboration, it's really about involving all forms of government and decision makers, again, as early, such as regulators, local, state and national decision makers in the communication and the discussions. One of the things that we've found in terms of going forward is really clarifying and defining your community. So particularly if we're looking at local industry and local precincts, think about your community, define it, and then you can pull together a regionalised focus from that as well. And you start thinking about not just the direct but the indirect benefits that can come from working together to try and achieve both your energy strategies and getting enough energy on board for businesses and the communities as well. And if you're working together to define your community with business and with industry, then you can actually start having really good conversations with them about how they can benefit and what their role is and what do they want. What do they actually want out of this transition? Data is really important in terms of collaborating. So we've worked really closely with particularly our major industrials in Tasmania to really understand their costs, the demand, the modelling, the supply scenarios, the timing. So you know where the constraints are, you know the production timeframes. And then as Ben mentioned before, without that, you can't plan. So you can't actually sort of work through bringing together both the government and government businesses who are trying to build the infrastructure to support. You can't actually get anywhere very, very fast without really good and honest data. And you have to have trusting relationships within that collaboration as well. One of the things in Tasmania, we might not have economies of scale, but we absolutely have economies of scope. So it's a little bit easier for us to bring together all of the relevant people within the local localised energy and localised area to really understand early on, as I said, around what could actually help. One of those things about data is I think we all need to agree data sources. So when we're collaborating and working together, communities get quite, or you will lose them very, very early if government's going out with one set of data, businesses are going out with another set of data, peak bodies are going out with another set of data. So what I have learned, it's really, really important to agree your data sources, check your assumptions, and then working together makes it a lot more efficient to do that scenario modelling. So you really do understand those economic and industry benefits and outcomes. And part of that is obviously communicating your expectations with each other and agreeing on those. And for us, it's being really clear about what we can do as government and what we can't do, and then moving on from there. So communicate, be honest, do it early, do it often, and have those really important relationships that you can really trust. It's pretty key.
Thank you very much, Kim. I think you summarized the points at the end of your talk as well, which was really good. Thank you. So I move on to you, Gus. So as the HILT CRC Research Director and also the leader of the decarbonisation scenario development for this project, my question for you is around the bigger impact of the outcome of this project, not only on heavy industry. Can you tell us a bit about what do you see as the outcome of this project would help all of the stakeholders, including heavy industry, government, and also an organisation like Australian Energy Market Operator, for example?
Yeah, thanks, Tara. Another good question. So obviously, what we're talking about is a lot of money that needs to be put on the table for both changing industrial processes or investing in some cases, new plant, or in some cases changing. It's on the plant side, but also on the infrastructure side. We know there's going to be significant more renewable electricity, but it won't only be electricity. There's likely to be fuels involved as well, and a number of options. And we need them to come together at the right time. There's no point in putting a lot of money on the table for electricity that goes in the wrong place at the wrong time, or how much do we need, etc. And for government none of this is going to happen without some government co-investment, and governments always co-invest in these kind of processes. They supported the initial, establishment of the initial steelworks, of new infrastructure, the electricity grids we have now. But for them to be able to justify that investment, they need to have independent information around what makes sense as to what to put where. So this is really why they're important, and they also help investors to have confidence that this is a good investment compared to other options. And what we're talking about is a field where there's a lot of change going on. There's new technologies potentially coming to the market. There's a lot of alternative ways of doing things, and so that's why they're important. And I guess there already are some scenarios that have been developed around the world. Of course, AEMOs already have their own scenarios they're looking for to guide their national planning processes, and there's other scenarios that have been developed. But typically what is done at the moment is they say, well, we have current loads in place A, B, and C. This steelworks around here needs this amount of energy. And then there's going to be some assumption, well, it's either we're going to have the same amount of energy, but it's going to electrify us. We need to now provide the same amount of energy that's provided by coal with electricity, for example. And then they just draw a straight line between, you know, where we are now and what's going to happen in the future. But of course, plants don't change like that. Every plant will have certain changes that will happen at certain time, depending on, you know, when the investment is and what's right for that place. And what's right in location A will be different from location B. So what we need to be able to do, of course, on the other hand, no one wants to be able to get involved in a company's process and try and get confidential information, because then you can't publish it. And it can't become public domain, because every companies have to maintain their own independent information, which is essential for investment and competitiveness, which underwrites our society. So what we want to do with these scenarios is develop, by enough knowledge of what goes on a certain location, to model simplified versions of real processes that account for enough of what's really there, but keep all the confidential details separately, and understand realistic ways in which processes could change or what investments might happen. And to get those realistic scenarios, we need to engage with industry, with government, with communities, etc., to understand which of these scenarios are plausible. So that's what we're developing through this multi-stakeholder process. We're developing plausible scenarios, and of course, each plant is different. It depends on the ore, it depends on what renewable resources or what other energy resources are at each location. So that's why we develop these scenarios that are informed by our stakeholders and really do have representations of what real plants are and how they could change. We also consider demand could grow. We could get improvements in process. They don't only have to add the cost. If there can be ways that can improve performance, they can attract investment and lower cost. So these are the scenarios that we need to develop. And then the models account not just for the energy, but also for the process, how they'll change, and they're linked together, because obviously if you're going to decarbonise by hydrogen from renewable electricity, you need a different set of infrastructure than if you're going to decarbonise from hydrogen from a different source, such as natural gas that's decarbonised, or if you're going to use some direct electrification pathways. So, and also the ability to account for technology changes that we don't know exactly when they come, but we can have informed decisions as to when they might become available, and provide guidance to how there can be flexibility in allowing for some of these emerging that may come in, and also represent what they might look like. So that's why the scenario planning is really important, because it helps everyone to have independent information. Of course, companies will not do exactly what these scenarios are, because it's a moving feast. But what it does is gives all parties, including society, the confidence that this particular pathway is a good one to invest in, government the confidence that they can justify why they should co-invest in this pathway, and also helps attract private investment, that these options, which consider the full end-to-end system of both the supply and the demand, that they can all be considered, and help provide independent information that's relevant to real pathways without actually trying to predict any futures or cut independent commercially sensitive information.
Thanks very much, Gus. Very spot on. Thank you. So I'm just a little bit of cautious of time as well for the next question. So if you can please be a little bit short and brief, that would be great. So my next question for you, Mitch, is about your current operations. So what are the primary energy sources and forms that you are currently using in your refinery? And which of these do you anticipate will be the most challenging to replace or decarbonize?
Yeah, thanks, Tara. That's a pretty big question, so I'll do my best to be
Yeah, I
succinct.
know.
So alumina refineries are rather complex and energy intensive processes. But yeah, I'll try to sum it up. So at Worsley, our refinery, there's two main energy demands, and they're both thermal. So one is the demand for steam at temperatures between 170 and 220 degrees Celsius, and then high temperature calcination, which approaches 1,000 degrees. In terms of energy sources at the moment, so the steam is generated predominantly from coal-fired boilers, But we are in the process of transitioning those over to natural gas, and we've already achieved 12% emissions reduction through that process. And so there's still more opportunity there. With the calcination process, that is already on natural gas, so there's less headroom there. And so we basically need to look at technology solutions to address that. In terms of the quantum of energy, in the last financial year, we use 48 petajoules of energy at the refinery, and 96% of that is in those two thermal loads from coal and natural gas. And the additional energy is in electrical demand for the refinery and the mine, and also some diesel consumption with the fleet at the bauxite mine as well. In terms of which is most challenging to decarbonise, I think steam and calcination are both challenging, but probably for slightly different reasons. So for steam, there's actually more mature technology solutions available, although there are still some other emerging solutions as well. But with steam, effectively, looking at electrification as the pathway, the main issues there are around integrating those options into a brownfield site. Space requirements and just the practicality of that. And then with calcination, because there's no real commercial solution to decarbonise calcination right now, it actually means that the option set is quite broad for that. But there's actually quite a lot of promising research that's taking place within the HILT CRC in particular. That research is looking to de-risk and scale up those solutions. But I think probably what's more relevant for this particular research project is a challenge that's universal for both of those energy demands that we have, and that's on the infrastructure side of things. So because of the scale of our energy demand, with those two loads combined, if we were to electrify that, we would have an electrical demand that's in excess of 1 gigawatt, and that's pretty constant. And to put that into perspective, we expect to rely on the Southwest Interconnected System, which is in the grid in the southwest of WA. And currently, the Swiss has a peak demand of 4 gigawatts. So if we add our demand to that, that's putting an extra 25% load on that grid. But then when you think about the fact that there's other heavy industry in the region that's also likely to electrify as well, you start to realise that heavy industry is likely to dominate the infrastructure requirements for the Swiss. And that is going to require a lot of strategic planning and very significant capital for the renewable projects to supply that and the infrastructure itself. There's also challenges on the electrical infrastructure side for the site implementation as well. But I won't elaborate on that just in the interest of time. But I do hope to talk about that at another upcoming webinar shortly.
Thanks very much, Mitch. So I'm just moving to the next question for you, Wayne. So how do you see the roles of electricity, heat, and fuels evolving at your site as you move forward to net zero emission? And what the specific energy infrastructure would be most critical for this transformation?
Okay, thanks, Tara. Look, I'll try and keep it brief. There's a lot more we could talk about here, but in essence, this is a really important reason why this project is here. All of these areas are vitally important, as well as other projects underway at HILT. And so for us, as an example, we're about to move from a transformation from an existing blast furnace facility to a natural gas DRI facility, EAF facility. And that means, just as a guide, when you do that, you're moving from an intensity of about 2 tonnes per tonne of CO2 to just using natural gas in a DRI facility to 1. So you half that emissions impact, which is substantial considering the volumes that we produce for Australia. And then when you move to natural gas or towards natural gas, you're around 0.5. So these are big steps. And so when you look at some of these fuels and electricity, natural gas, hydrogen, electricity are big. But there's also the step further beyond that, and also steps to support that process in itself. So it means when you start to look at the other areas around heat reuse, storage, circulation, what processes you use it in, other fuels, other technologies for electricity, other technologies for hydrogen, all of these become very important, particularly when you want to then apply them. How do you apply them? When do you apply them in the process? Do you apply them for reheating? There's all of these dimensions, from the process heat management, storage, utilisation, from the fuels and how you reuse them, how you relook at them, the logistics around this. So you're moving, as I mentioned before, away from a market based on coke and coal and shipping in coal to no longer shipping it in, but piping in natural gas. So there's logistics changes, storage changes, market changes. And then, of course, the new technology or new ways of looking at electricity and how you optimize that. So there's a lot there. So it's important to look at it holistically, but also individually in each of these areas. And so the role that this kind of project helps with those big rocks or those big jumps, but also on the next step, how do we get towards that net zero future as well?
Thanks very much. So I'm moving to you, Ben. So my next question for you is about Grange decarbonisation strategy for the pellet kiln is to transition from anthracite and natural gas to hydrogen or electrification plus heat recovery. So what are the most promising near-term technologies for this transition? And what is the technology that require longer-term research and development?
Sure. Yeah, so anthracite, obviously type of coal, helps us increase the energy and the heat in the furnaces. So generally without that, you can only get it to a certain degrees. We need that to get it to 1250 degrees basically. So we've actually we've got 5 furnaces, and we've actually converted one of our furnaces to not run with anthracite. It's called an intermediate air project, and that's successfully getting the same production rates and quality standards as far as cold compression strength and the likes. So we're confident that we've now got a furnace running just on natural gas without coal, and we're about to roll it out to our remaining 5 furnaces by 2029. So we're already on that journey. As far as gas, that's a hard bit. You know, we've done technical and commercial feasibility studies to look at hydrogen, which was half funded by RecFit, so Kim and her team. So helping funding studies is really good to get us the information and the data to make decisions. So yes, it's technically feasible, we concluded, but obviously commercially way out. And there's additional engineering that's required to look at the burners and upgrading your burners to handle hydrogen. It's possible, but you need to work with the OEMs to spec that up. Yeah, and we've got 5 furnaces that we only run 4, so we've got the benefit of having a spare furnace that we can run demos on. And I think that's a very important concept people forget, is that you can't just try and prove up a concept on paper or basic tests and then change the whole business, because you potentially break it, because you may not get the throughput, you may not get the quality outcomes. And I think others have sort of looked at that, like brickworks and likes, and maybe hydrogen's not going to produce quality bricks, so biogas is better off. Yeah, and the heat recovery, that should be a no-brainer if you can capture it at cheap enough, right? So we lose so much heat on our conveyor systems, it's not funny. So by able to circle that back in, whether it's via an inline cooler or an annular cooler, depending on what works best. So we're obviously reviewing that and looking to expedite that project next year, and there's some funding that maybe we can get around that. Electrification is a little bit harder. You can only really get those panel heaters up to about 850 degree. We need to get 1250, so you still need your natural gas or your hydrogen or even plasma, which is a bit expensive, to get you to those levels to cook things properly. So yeah, and look, I guess it also forces you to look at the product that you're producing too, and could you do that different? So there might be opportunities to look at coal bonded pellets in the magnetite space that only require about 150 degrees and heaps less energy. So yeah, there's sort of things we're looking at to look at technologies, and certainly costs come down on hydrogen. I think that will be a game changer.
Thanks very much, Ben. So I'm just moving to the next question for you, Kim. So a question is about the the change in the policy. So what is the specific state level policy changes? So for example, around the planning scheme and permits are most critical for accelerating delivery of the energy and industry infrastructure we need for this transition.
Yes, good question. I will be brief as well. From a policy and regulatory perspective, I would say there hasn't been a magic answer, but everybody's working on how we might be able to do this. As I said before, the state doesn't hold all the levers. We wish we did, but accelerating the development, I think, absolutely depends on understanding what you can change early. We went early on safety legislation to make sure hydrogen was captured, which has helped accelerate some of our domestic market hydrogen projects. I do like to remind people that laws are there for a good reason, and that our policy and our regulatory environment really needs to start looking at market failure. One of those elements in Tasmania was that we moved pretty quickly to automatically designate major energy projects as major projects under our planning laws, which saved 2 to 3 months. It doesn't sound a lot, but it is if you're working on the early stages of projects. The other thing that we're trying to do is our benefit sharing framework. So we've got a pretty clear policy on that. I'd like to see it embedded a little bit more. We're only, again, at the early stages of implementing that across our renewable energy zones in Tasmania. But the other side of that needs to be better engagement from a policy perspective with local Tasmanian Aboriginal communities as well. So I think that from a policy perspective, you can work across a lot of different elements of the approval chain, of the supply chain, and of the regulatory changes. But you need to definitely balance speed with social license, which is why we sort of hit on the safety standards first. One of the key reform areas we've been thinking about, actually, some of our pre-zoned industrial energy precincts like Bell Bay, up in Burnie, and in Brighton, where we've got industrial hubs. And that's where heavy industry, ports, grid infrastructure already exists. So I think we've been trying to work on, where we've already got, rather than greenfield sites, some already zoned spaces, and how we can accelerate and focus some of the renewable energy developments in those zones, like our green hydrogen hub. But I'm going to run out of time. I've got a lot more to say, but maybe for next time.
Thank you so much, Kim.
Check out our website, it's great.
Thanks. Thank you. So my last question is for you, Gus. How do you ensure that the scenario that we are developing as a part of this project are both technically realistic and at the same time ambitious enough to meet the net zero target by 2050?
Yeah, thanks, Tara. So I've already mentioned that a critical part of developing our scenarios is to engage with all types of stakeholders. That's industry, government, community, etc. So that's obviously really important. We make sure the scenarios end up at net zero. So that's ones we're looking at the moment, all the net zero 2050 scenarios. But the other critical bit of the puzzle is really making sure that the models are realistic, while being sufficiently simple enough to calculate. You have to have simplifications in any system, and when you're looking at the whole system of energy and infrastructure, then you need ways to check it. So the other critical part of that is that within HILT's framework, we have some 60 industry partners, and that includes not only industry that are in the production side of the steel and alumina that we've talked about here, but also cement and lime, for example. But also we have technology providers, engineering companies such as Worley. We have got also AEMO and other government partners in that as well. So as we develop models, we can then draw on our industry partners to help cross-check the validity of our assumptions on the costing, etc. Not that they're necessarily, nothing's exact, because you're talking about projections in the future, but we can check that they're realistic and sufficiently realistic to make sure that the relative systems we're evaluating are reasonable. So I think, without going, because we're running out of time, but that's really the main point I'd like to bring in, that having this wide range of industry stakeholders is really critical for making these assessments realistic.
Thank you very much, Gus. My apologies again for running a little bit over the time. Just I would like to thank everyone again for your time and for your contributions and for your valuable insight. So I think I'm just wondering if we can maybe answer one of the questions, if we can do that very quickly, because if there is one question from the audience, it's about the large industrial have developed a huge knowledge based on decarbonisation planning and pathways. What do you think are the most important tools and support for smaller industry facilities that are not as far progressed on their net zero journeys? So if anyone wants to just quickly maybe address this question, because we try to answer some of the other questions that we had in the chat. Anyone has any opinions on this?
Yeah, I'll jump in, Tara. I guess I would just offer a suggestion to, I guess, tap into the networks that have been developed already. There's a lot of really strong collaboration going on. I guess with those larger facilities and research organizations and technology providers. I think there's a very good ecosystem of people that are really happy to collaborate and share knowledge and insights that I think would help smaller facilities.
Thank you very much. Thanks everyone again for attending this webinar, and thanks to our panelists again. And again, apologies for being over time. Thanks and have a good rest of the day.
Thanks, everyone. Keep up the good work.
Thanks, Tara. Thanks all.
Keep up the research. It's very important.
Sure.